Welcome to section 3.2. We're using substitution and elimination to solve systems. So we were solving them in section 3.1 by graphing our tables. We saw that wasn't very reliable. So we're going to be using substitution method or the elimination method, which is a more reliable method. And we're going to start with the substitution method. So we're going to solve this equation. Y equals 2x minus 1 and x plus y equals 5. So remember, ordered pairs have to satisfy both. And if we look at this top equation is almost a formula for y. It's a formula for y. So we're going to take this y, and since the y values have to be the same for both solutions, we're going to substitute it in. All right, so it's going to look like this. We're going to have x plus y equals 5. But by substitution, remember the y is 2x minus 1. By substitution. All right, so notice now we have an equation just in terms of x. So now we can actually solve this equation for x. Solving linear equations, we get rid of our parentheses first. We combine like terms. All right, x's stay on one side, y's get moved, or constants move to the other. And then once all the variables are combined on one side and the constants are combined on the other side, we divide by the coefficient. And so we're looking at x equals 2. Okay, so that's our solution. X equals 2 will be a solution to the system. But remember, solutions are ordered pairs. So whenever I solve a system like this, I always like to write out an ordered pair. That way I won't forget that I need two components. I need an x value and I need a y value. Okay, so how are we going to get the y value? Well, remember we have a formula for y. Y is 2x minus 1. So let's bring that back and we're going to write y equals 2x minus 1. And we're going to find the y value when x is 2. So when x is 2, y is going to be 4 minus 1 is 3. Okay, so now we have our ordered pair. Let's put the 3 up where it belongs. And our solution now is 2, 3. 2, 3 is our solution. Let's check our work. We check our work by making sure that ordered pair 2, 3 works in both equations. So first we have y equals 2x minus 1. And this is the equation we used to find y, so we kind of already know it's right, but 3 is equal to 2 times 2 minus 1. Correct. And now the other equation, x plus y equals 5. Does 2 plus 3 equal 5? Yes. So since these are both true, 2, 3 works for both, so now we know it's a solution. All right, so that's essentially how we're going to be using our solutions, or substitution method. Let's look at a more complicated example and write out the steps of the substitution method. All right, so we're going to solve this system. And our first step in solving this system is to isolate a variable in one equation. So let's look at our system. If we had to solve for a variable, what would be the easiest variable to solve for? I would say this y, because the coefficient of the y is 1. Okay, so I'm choosing y just because it seems a little bit easier to me. Okay, so I'm going to rewrite that. 2x plus y equals 2. I'm solving for y. That's isolating a variable. So subtract the 2x. So y y equals negative 2x plus 2. Okay, so we can also write it up here right next to that equation. So the top equation is the same as negative 2x plus 2. And I like to do that because I like to use arrows. And now I'm going to take this equation and I'm going to plug it into the new equation. And that's step 2, substitute into the other equation. So 5x minus 2y equals negative 13. But we're saying that y is negative 2x plus 2 from the other equation. All right, and remember both y's have to be the same because we're finding solutions. That's why this works. All right, now we have an equation in one variable x. It's time to solve. How we solve linear equations is we get rid of our parentheses first. So let's multiply negative 2 times negative 2x and negative 2 times positive 2. All right, then we combine our like terms. 5x plus 5x, just add the coefficients. 9x minus, whoops, did you guys catch my mistake? 2 times 2 is 4. Sorry about that. Okay, carrying on. Minus 4 equals negative 13. Move the constants over, so add 4 to both sides. All right, so the signs are opposite, so we're going to treat it as subtraction. The bigger number is negative. And then divide out by the 9. Negative 9 over 9 is negative 1. Okay, so remember that's half an equation, or excuse me, half a solution, because a solution has to be an ordered pair. So now step 4 is to find the other variable, the other coordinate, and substitute back by substituting back into one equation. So we can choose either equation. It doesn't matter. We can either choose 2x plus y equals 2, or 5x minus 2y equals negative 13. But remember, we already have a formula for y. We already determined that y is equal to negative 2x plus 2, so let's use that. We've done all the hard work already. So what's the y value when x is negative 1? Negative 2 times negative 1 is 2. 2 plus 2 is 4. Okay, so we have our ordered pair. Our ordered pair is x equals negative 1 and y is 4. All right, and then how we check is we're going to check by plugging in the ordered pair solution to both equations. Again, we already know it works for the top one. So we can try to see if it works for our second equation, or 5x minus 2y equals negative 13. So negative 1 for x and 4 for y. All right, negative 5 minus 8. Negative 5 minus 8 is negative 13. So we know we did this correctly, so we're good to go. All right, so with that, let's try to do some of these on our own. Now that we know that basic process, go ahead and push pause, and then come back and see how you solved example 1. All right, let's see how you guys did. So substitution method, you guys are finding a variable to solve for. This x right here has coefficient 1, so we can add 3y to both sides and get an equation for x. And now we're going to plug it into the other equation. So this x right here is going to become 3y plus 4. All right, so a nice substitution method. Now we have an equation in y. So to solve it, we distribute our 2. We get rid of our parentheses first. We combine like terms. 6y minus 5y. 6 minus 5 is 1. And solve for y. And y equals negative 3. This is half a solution. We have an equation for x. Let's plug in the y equals negative 3. And solve for x. We get x equals negative 5. And here's our ordered pair. All right, let's look at some other examples. And this one has a bit of a twist, so let's see what happens. So when we plug in y, we get 6x minus 3y equals negative 3. All right, so far so good. Let's solve for x. So get rid of our parentheses. By distributing that negative 3. Combine like terms. Oh, what's 6x minus 6x? It's 0. So that goes away, and we're left with negative 15 equals negative 3. All right, so a couple observations. We ran out of variables. All right, so write yourself these notes because when we run out of variables, like we have here, negative 15 equals negative 3, we have two special solutions. We have to check if the statement is true. So if there's no variables, we ask ourselves, is it true? And in this case, no, it's not true. Negative 15 does not equal negative 3. So what this is telling us is no matter what we plug in for x, it's never going to be true. No matter what we plug in for x, it's never going to be true. So nothing's ever going to work. So no ordered pairs work. So no solution is the answer. And if you remember, no solution from the previous section, that means we have an, whoops, I wrote consistent. We have an inconsistent system. And do you remember when that happens? When we have parallel lines. All right, and check this out. So here we have y equals 2x plus 5. I'm going to take the 6x minus 3y equals negative 3. I'm just going to quickly solve it for y. So a little scratch work, bonus round. So subtract the 6. Divide by the negative 3. Remember, dividing by negative changes all the signs. Okay, so y equals, let's see, negative 6 divided by negative 3 is 2x. Negative 3 divided by negative 3 is 1. All right, so our second equation is y equals 2x plus 1. And notice we have the same slope, different y-intercepts. Those are parallel lines. Parallel lines don't have solutions. All right, and we didn't have to do all this. We know they don't have solutions because when we try to solve it, the variables disappear and it's not a true statement. It's false. Nothing will ever work. No solution. Parallel lines, they never intersect. All right, so all of this good stuff. Parallel lines never intersect. No solution. Let's look at the next example. We're going to solve. Again, substitution. Let's use substitution. Y is already solved for. We can plug it directly into that second equation. So 2 times y, but y from the first equation, whoops, that's a typo. The x is not in the denominator. Don't do that. It's 1/2 times x plus 3. So 2y minus x equals 6. All right, so let's solve this. So clear your, or get rid of your parentheses by multiplication. 2 times 1/2, the 2's cancel, plus 3/2. Oh, I'm so sorry. Plus 2 times 3 is 6, minus x equals 6. And again, when we combine our like terms, x minus x is 0. So again, we're in this situation where we don't have variables. So let's write ourselves a note. No variables. Our variables went to 0. So it's a special case. Is it true? Does 6 equal 6? Yes. 6 equals 6. So what this is telling us is no matter what we plug in for x and y, what ordered pair works for the top one, what one works for the bottom, it's always going to be true. So this is telling us it's going to be infinitely many solutions. All right, and in that case, this is the one where it's the same line. Infinitely many means we have the same line. And if we go back up and solve for y here, we're going to get y equals 1/2 x plus 3. And I'll let you guys verify that too. So a couple of statements. You guys can write infinitely many. You guys can also write something like the solution is all ordered pairs that satisfy one will satisfy the other. All right, there you go. Okay, so whenever we don't have variables, it's either going to be no solution or infinitely many solution. And it all depends on whether or not the numbers are a true statement. Okay, so there are some limits of the substitution method. For instance, let's take a look at this one. Let's say we're asked to solve this. If we choose any variable to solve for, we're going to end up with really horrible fractions, right? So the limitations of the substitution method is sometimes we can get really ugly fractions that can sometimes be hard to work with. So we can write that down. Sometimes solving for a variable complicates things. Okay, so we need another method because it's all about being efficient. And the next method is the elimination method. And we eliminate a variable using addition. And we do this kind of thing when we solve equations, solve linear equations, and we move terms on the other side of the equal sign. We do that by eliminating that term. So for instance, if we wanted to eliminate 4, we would subtract 4. If we wanted to eliminate -5, we would add 5. All right, so we're talking about additive inverses. And it's the same thing, and we eliminate a variable using addition. So actually, to be more precise, we can add a negative version. That's really what we do. That's what subtraction is. It's adding negative numbers. Okay, so let's see a really basic example of the elimination method, and then we'll look at something more complicated. In this example, we're asked to solve the system, and I'm looking at the 3 and the negative 3, and I know those are additive inverses. If we add 3 and negative 3, it goes to 0. So what we're going to do, we know that when solving equations, we can add the same thing to both sides, right? Since everything is equal, adding up these equations side by side is still obeying all of our properties of solving equations. So look at, we're allowed to add equations as long as everything is lined up. So all of the x's are lined up, the y's, the equal signs, the constant. So let's add everything up. 3x minus 3x is 0. That's why this works. 5y minus 2y. And 26 and 2. All right, and that was really fast. And now we have our equation in one variable. We can solve for y by dividing by negative 7. 28 over negative 7 is negative 4. And then how do we find the x? We just take the y equals negative 4, and we can plug it into either equation. The bottom one looks less intense to me, so I'm going to plug it into the negative 3x minus 2y. Okay, subtract that 8 and divide by negative 3. And then you have your ordered pair solution to negative 4. All right, so the elimination method. Let's look at something more complicated, and we'll draw this out step by step. All right, so we're going to be solving 3x minus 2y equals 7. First thing we do is we look at our system and we choose a variable to eliminate. Okay, so remember we have to make additive inverses. 3 and negative 6, well, I know 3 times 2 is positive 6, so I can make an additive inverse by multiplying 3 by 2. Over here, let's see, the smallest number 2 and 5 go into is 10. So I'd have to multiply 2 by 10, 2 by 5, I had to multiply 5 by 2. Now I have my additive inverses. Strategically, the x is easier. So we're going to choose the x. That's our first step. All right, multiply each equation if necessary to make the coefficients additive opposites. Well, in this case, we just have to multiply 1. And they're already opposite signs. The top one is going to be positive 6, the bottom one will be negative 6. All right, so we actually multiply both sides. After we distribute, that's like multiplying every term. So we have to multiply by 2 3 times. All right, then we add up our equations as before. By design, one is going to go away, one variable is going to go away. So in this case, we're left with negative 9y equals you know what? And it's going to be equal to 19. And I'm actually going to change it. Sorry, I just realized there was a typo. So go back. This is actually a 4. Not bad, not bad. Negative 6x minus 5y equals 4. Sorry about that. Now it's 18. I just saved us from some pretty horrifying fractions. All right, divide by negative 9, and we get negative 2. All right, so that's step 4. We just solved for negative 2. Now we're going to substitute into equation to find the other variable. We can do the top or the bottom. It doesn't matter. I'll use the top. 3x minus 2y, but remember, y is negative 2. And this equals 7. So get rid of your parentheses, do that multiplication. Negative 2 times negative 2 is positive 4. Subtract the 4. and divide out by the coefficient. So 3 divided by 3 is 1. All right? And now we have our ordered pair solutions. So let's go ahead and check our work. We use the top equation to find our ordered pair. So now let's use our bottom equation to check. So negative 6x minus 5y should be 4 after our edit. And negative 6 plus 10 is indeed 4. So we're good to go. And that's how we're solving systems using the elimination method. Okay, so let's continue onward. We're going to be solving this equation. And before you guys push pause, remember back to your algebra class. We haven't talked about it so much in this class. Whenever we have fractions in an equation, the only reason why we can do this strategy is because it's an equation. We know we're allowed to multiply both sides by a number. So to get rid of all of our denominators in this first equation, notice if we multiply every single term by 6, which is allowed because it's an equation, all of our fractions go away. We can multiply by the LCD. Same thing, only because it's an equation, we're allowed to multiply both sides by the same number. If we multiply by the LCD, the fraction's clear. What is the LCD? It's 4. Okay? So let's see what that looks like. So we're going to multiply the top by the LCD, which is 6. You can write it as a fraction if it helps you clear your denominators. And multiply the bottom by 4. I'll write it over here. Okay, so let's remind ourselves how to do this. We'll go slow. So remember multiplying both sides after we distribute everything. It's like multiplying each term by 6. So I'm writing out the equations without multiplying anything first. Okay, so we're going to multiply each term by 6. Multiply each term on the bottom by 4. Okay, and now let's start canceling. In the top, the 3's will cancel. 6 divided by 3 is 2. 6 divided by 2 is 3. And then the 6 is straight cancel. All right, and then similar stuff to the bottom. So when we have an equation with fractions, we multiply both sides by the LCD. All right, let's see what we're left with. The top one, 2x times 2 is 4x. Next, we have a y times 3. And then a 1. All right. Second equation. We're left with an x and a 2. We're left with a 5y. And we're left with an 11. So notice this is a lot easier to work with than working with all those fractions. Okay, so it's a little bit tedious, but it's worth that extra step. All right. So how would we solve this? Let's choose a variable to eliminate. I would say these would be easier, the x coefficients are easier to turn into additive inverses. So I would have to multiply 2 by 2 to make it an additive inverse. It has to be the opposite sign. So let's multiply it by negative 2. And both sides, that's the same as all terms. So 4x plus 3y. And then multiplying all terms by negative 2. We get this. And how we design it, when we add it up, a term should go away. All right, and then 3 minus 10 is negative 7. Y. And 1 plus negative 22 is negative 21. So divide by negative 7, and y is 3. All right, so let's figure out what the x is. So I'm going to plug in to the bottom. So 2x plus 5 times 3 equals 11. 2x plus 15 equals 11. Subtract that 15. And x is negative 2. So we can write x as negative 2 and y is 3. And then there's your solution. All right, let's look at another example. So you guys can pause it and then come back and see how you guys did. All right, in this example, you had to multiply both equations. So again, we can look at the 6 and 9. What's the additive inverse there? I guess the smallest one would be 18. And between 5 and 4, that would be 20. So you can work with either one. I'm going to choose 18. So I'm going to multiply the top by 3. And I'm going to multiply the bottom by, I'll say, negative 2. Okay, so let's write our new system. So remember to distribute that 3 and that negative 2 to all 3 terms. So 6 times 3, 5 times 3, and 13 times 3. And on the bottom, 9 times negative 2, 4 times negative 2, and 2 times negative 2. Okay, let's add it up. 1 goes away as designed. We're left with 7y equals 35. So divide out by that 7, y equals 5. All right, lovely. Choose an equation to plug it in. I'll plug it in the bottom. 9x plus 4 times 5 equals 2. PEMDAS, multiply first. Subtract that 20. And divide by 9. All right, and then we have our ordered pair. All right, some more practice. This one is a decimal. Just like fractions, we can get rid of decimals. Notice we have just a tenths place. And we know by multiplying by powers of 10, it moves the decimal to the right. So if we wanted to clear the denominator, if we wanted to clear the decimals, since we just have a tenths place, we can multiply everything by 10. So some people like to do that if they really don't like to work with decimals. And you have to move all decimals to the right. And it's just a strategy. Okay, now we don't have decimals. All right, so we can multiply the bottom by positive 2 to get our additive inverses. And I chose y because we already have opposite signs. So it's one less thing for me to worry about. Those cancel. And we get x is equal to 3. Plug it in to figure out your y. And then you get your solution. Subtract that 9. All right, remember to write as an ordered pair. Okay. Our next example, and here we go. Our next example, nothing's lined up. So before we start, we have to get rid of our parentheses, gather everything together, and line up all the x's and y's and the constants. So take some time, distribute all of your 2's, -3's, -4's, and 5's, and come back and see how you did. All right, so I wrote the top equation in blue, the bottom one in red. Just distributed, combined those like terms, and then I lined up everything, right? So I moved the constants to the right, so the x's are lined up, the y's are lined up, equal, and constants. And now we're ready to solve. And I would solve this by multiplying by 2. So go ahead and push the pause button, and I will put up the rest of the solution for you to check out. All right, so let's just take a moment. You can pause and just kind of go through your solution. Okay, so final example, sometimes we ask, what's the best way to solve a solution or a system? Because we have 3 different methods, substitution, elimination, or graphing. So essentially, if things are lined up, like we have right here, if things are lined up, like right here, and solving for a variable would be difficult, elimination's the best method. If we're looking at a system and a variable is already solved for, like right here, substitution would be the best way. So take a moment. We are going to finish up this problem. You're going to do it on your own and then just kind of reflect on what you think of the various methods to solve our system. Whew. All right, so lots going on here. So substitution, you plug it into the top equation and you solve for your y. Once you solve for y, you plug it into one of the equations. I did the equation for x equals 5 minus 2y, and you get x equals 1. All right, and substitution was ideal because x was already solved for. If we wanted to use the elimination, we have to line everything up. So I had to move the x to the x column, add 2y to both sides before I could even start the elimination. And then I multiplied by -2, right, added them up and got my y equals 2 just as before. But it took a little bit more work because it wasn't set up to be elimination. All right, and then we carry on before. We can plug in x equals 2. Graphing was even more clunky. I chose to take both of those equations and write them in slope-intercept form. So here's the top in slope-intercept form. I had to do a little bit more work on the bottom. All right, and we graph each of those using the slope and the y-intercept. And point of intersection is the solution. And again, we get 1, 2, but we had to do a little bit more work versus just the substitution method. All right, so that's how I compared the results. You guys can write that down in your own words. And then using that information, we can talk about a one-solution system, so intersects once. That would be easiest to solve by substitution. And maybe that would be one that had a variable like x equals 2x minus 5. Easier to solve by elimination is if we have everything lined up, maybe the coefficients aren't equal to 1. So it's easier just to do our elimination method. And maybe it'll be easier to graph if everything is in y equals mx plus b form. Something like that. So these answers are going to vary. Try to verbalize what we were just discussing.